Hello friends, welcome to CEC Live Lectures. Dear friends, as you know that in our previous session yesterday we talked on one of the important analysis, that is factor analysis, and today we are going to talk on regression analysis. Once again, we would like to tell you all that it is a part of our series on business research methods. Friends, on today's discussion, we are going to learn a lot because we have with us in our studios Dr. Namita Rajput. Dr. Namita Rajput is principal in Sri Aurobindo Evening College, University of Delhi. Dr. Rajput is a dynamic professor who believes in giving her best. She has authored numerous books and she has participated in various conferences and seminars at a national and international level, and we believe that her experiences will help us out in understanding in today's topic in detail. Friends, if you want to ask questions from Dr. Namita Rajput on today's topic, then do call us through our toll-free number. Our number is 1800110430. I repeat, our number is 1800110430. Now, I would like to welcome our guest, Dr. Namita Rajput, and I would like to request her to explain us in detail what regression analysis is. Hello, ma'am. Welcome to the lecture.
Good morning, friends. We have already talked about the correlation and a little bit of the conceptual framework of regression. So as you all know, regression is a technique to have a basic insight of cause and effect relationship. So we would be moving further with the models of the regression because the basics have already been covered in the previous lectures. So the general form of classical linear regression model is equal to y is equal to alpha plus beta xi plus error term, and I goes from 1 to n. Please be very careful in listening to this classical linear model, because this is the model which is fairly largely and happily used in many of the economic problems, in many of the research problems. So that means on the right hand side we have the independent variables, and on the left hand side we have a dependent variable. So yt is a dependent variable, whereas alpha, beta, xi plus error term is the independent variable. That is, any changes in all these will make a change in the yi. In the above equation, it is called as a simple linear regression model. Also, it is called as a two-variable linear regression model, where alpha is called as the intercept parameter, beta is called as a slope parameter in the relation between the variables x and y. Ei is also called as the error term or disturbance term or a noise term. So taking this into consideration, that we have identified two major factors because of which there is a change in the yi, but we have already included the error term because there are certain factors which are not measurable and which is, because of the miscellaneous factors. So we, to make a model more comprehensive, we always add the error term. So that is how we have added here the ei, because there are certain factors which are, because of certain noise factors, because of certain disturbance factors, brings about a change in the dependent variable. So we have now talked about a simple linear regression model or a two-factor regression model, two-variable linear regression model, and you have already seen the equation, that is yi is equal to alpha plus beta xi plus ei, where I goes from 1 to n. Now we would be talking about certain assumptions of the classical regression model. Zero mean of disturbances. So we have the first assumption of the classical regression model is that we take zero mean of the disturbances, that is the error terms which we have taken into consideration. The zero mean of disturbances, that is zero for all i's, that is whatever is the error term mean is always equal to zero. This is the most important assumption of the classical regression model, followed by homoscedasticity, that is the variable ei. The variance square is a constant for all i's. So you have seen here that we are taking into consideration the assumptions of the classical regression models, and both the first and the second assumption they are centering around the error terms. The first said that the mean of all error terms is equal to 0, and the homoscedasticity means the variance of the error terms is always constant. Next is a non-autocorrelation, that is the error terms are not correlated to each other, that is EI and EZ is equal to 0 if I is not equal to J. So that means the non-autocorrelation, the covariance of all the error terms is equal to 0. Uncorrelatedness of the regressor and disturbances is also equal to 0, and normality is equal to 0 and variance. The non-stochastic regressor, that is the value of xi, is also called as a constant in the probability distribution of yi. So we have seen here about various meaningful assumptions of the classical linear regression models. So let me give you a recap. We have the zero mean of all the error terms, that is equal to 0. The variance of all the error terms is also equal to constant, and of course the non-autocorrelation is there between the covariances of the this error terms, that is the EI to EZ, followed by the normality, and non-stochastic regressor, that is the value of xi is known to be constant in the probability distribution of yi. We have used ordinary least square method to estimate the parameters of the model. The ordinary least square equation we have already talked about. So it has certain parameters. For a parameter to be blue, the blue says what? They are L stands for linear, U stands for unbiased, E is efficient, C is consistent, and 5 is sufficient. So if the parameters are having all this, we call it as a blue parameter. Then we talked about statistical properties of the parameters of the model. The statistical behavior of ordinary least square methods. If alpha and beta are the estimators of alpha, alpha hat and beta hat are the estimators of alpha and beta, then these estimators follow a normal probability distribution. I repeat, if alpha hat and beta hat are the estimators of alpha and beta, then these estimators follow a normal probability distribution. Their parameters are E alpha hat bracket close is equal to alpha plus variance of alpha hat is equal to summation of xi square upon n sigma xi square into variance square. Similarly, for the E beta hat is equal to B and variance of B hat is equal to variance upon summation of xi square. So these parameters, these formulas must be very clear to the researcher to find out the statistical behavior of the ordinary least square method estimation. Now, what is the concept of a linear? The issue is linearity in variables versus linearity in parameters. We also study what's the impact of scaling and changing measuring unit in OLS estimates. Change in measuring the unit or scale of variables, estimate of alpha, estimate of beta, standard error of alpha, standard error of beta, and the R square. Increase in X if it leads to no change, decrease by the same factor, the standard error of alpha is no change, the standard error of beta is decreased by the same factor, in R square there will be no change. Followed by, if there is increase in only Y, this leads to increase by the same factor, increase by the same factor again, increase by the same factor, increase by the same factor. So that means R square will also, there will be no change. If there is increase in X and Y both, so there is increase by the same factor, in estimates of beta there will be no change, in standard of error of alpha there is an increase by the same factor, the standard error of beta will also not change, and also the R square will also remain constant. Now we are coming on to a multiple regression model. In the first slide, when we started with the presentation, we had a 2-variable regression model. but here we are talking about the multiple regression model. So that means we have n number of variables into the regression model. So now the equation will be extended as follows. The yi is equal to alpha plus beta xi plus beta 2x2 plus beta kxk plus error term, that is the ei, and I goes from 1 to n. So there is a simple extension of the two variable regression model that we have added into this, the n number of variables, and the alpha is again the intercept of the parameter. The bi is the slope parameter in relation to variables x and y and x. Ei is the error term, disturbance term, or a noise term. So we are taking into consideration now the multiple regression model. The multiple regression model, there are basic assumptions which we have to understand. The assumptions are as follows. The zero mean of disturbances, again 0 for all i's. Homoscedasticity, that is the variable xi, is a variance square, a constant of all i's. The non-autocorrelation, that is the covariance of the error terms, is also equal to 0, that is I is not equal to j. And uncorrelatedness of the regressor and disturbances, that is the covariance of xi and ez, is equal to 0 if all i's and j's. And another is the normality, that is ei is they follow a normal with the zero mean and the constant variance. Non-stochastic regressor, the value of xi is also known as inconstant the probability distribution of yi, and xi's are not linear function of other explanatory variables. So after we have tried to get deeper understanding about the multiple regression, let us try and understand the basic mean dynamics relating to it. Now this deeper understanding will help us to take care of the control variables, moderating variables, and mediating variables. Though multiple regression models, we have to understand these three concepts, that is the control, moderating, and mediation variables. To appreciate how to take care of the control variables, let us consider the following example. A company wants to find out the impact of its advertisement expenditure on its sales. That is, if the company has a basic understanding that the company is spending so much on the advertisement, does it impact the sales or not? So this is the question which the companies have to find out. Let us have a look on this. The data about sales and the advertisement expenditure was collected, and the following scattered plot regression results show some relation between the two. So here we are talking about the dependent variable is the sales, independent variable is the expenses, and the method which we have used here is a least square methods. So observations are as follows. The variables are advertisement, the coefficient, standard deviation, t statistics, and the probability. So if you see the probability, it is coming on to be 0.05. The t statistics is also near to 1. So that means the regression and the adjusted regression, the data is about the sales and the advertisement expenditure was collected and plotted on the scatter plotter diagram. The regression results show as follows between this thing. So what is the observation which you have seen? Because the probability is coming on to be less than 0.05. So it was observed that during the period of advertisement expenditure, the prices have increased, resulting into lower sales because of the negative relation as shown in the following scatter plot. As you've seen, the line is scrolling down from left to right, which means the changes in the prices are blurring the relation between the sales and the advertisement expenditure. The challenge is now what? The challenge is about how to control the effect of prices while determining the relationship between sales and expenditure, advertisement expenditure. So here the problem is, the different. That means we are here trying to find out the relationship of whatever are the expenditure spent by the company on to increase the sales. So you are trying to infer that what is the impact of sales because of the rise in the expenditure, but there are certain changes in the prices which impacts their relationship. Now the challenge is how to find out that relationship which we are trying to infer. So here we have to appreciate the control variable. So that means we have to control certain variables to find out the real relationship between the other two variables. Because if all the variables are in action, we will not be able to find out anything. So here the question of control variable comes. The control variation is a variable that is held constant in order to assess or clarify the relationship between the two other variables. We have to filter out the effect of such variables to establish the relation between the other variables also. So the control variable should not be confused with the controlled variable, which is an alternative term for the independent variable. So now the question is that if we are not able to have any kind of control over the prices slashing, so we will not be able to infer the right kind of a relationship between the expenditure which has been spent by the company on to the sales. So here we have to either control certain variables to find out the exact relationship between, if the company is spending on the advertisement, what is the impact of that on the sales. So because of which the question of the control variable came, and the control variable is about the prices controlling. Because if you are not able to control the prices, there will be impact on the sales itself, and we will not be able to infer the right kind of relationship between the advertisement and its impact on sales, because on the other hand of it, the prices are slashing or increasing, which is impacting a clear cut on the sales. So here the question of the control variable comes. So just have a look on this. The following regression model, the prices are introduced as a control variable. We can see here, otherwise the dependent variable is sales, independent variable is advertisement, and we have seen the probability is 0.0080 in the first column. That means it is significant, whereas the price is -7, and also the probability is significant. The regression and the adjusted regression is about 44 and 43%. So here what are we trying to infer? So here, how do we decide which model is a better model? How to decide which model is a better model? The indicators are as follows. So we have seen a table in which the 4-5 parameters are mentioned, that is the R square, the probability and the T statistics. The probability, if it is less than 0.05, it is said to be significant, and the T value, the thumb rule, is near to 2. So the thumb rule is that if the T statistics is near to 2, 1.98 or 1.28 or 2.0, that means the model is significant model, because the T and the P, they move on an opposite direction, because the P is has to be less than 0.05 at 5% level of significance, followed by a T thumb rule, that is it has to be near to 2. So these are the thresholds which makes the model more significant, and this is what you have to interpret when you are writing about the interpretation of your research problem. So now coming on to the following could be used as the best purpose to find out which model is a better model. Suppose we have two models in front of us, model 1 and model 2. So which one is a better model, model 1 or 2? So we have to see two indicators. The first is adjusted R square, and the second is the standard error of regression. And of course, when you are doing a hypothesis testing, you have to see the overall F statistics followed by T test for the individual estimates. So let us have a look on this. We have also learned about the gender bias in the wages in India. That is, if you talk about the male and the female wages, the male gets more wages and the female gets less wages. The impact of the booms and the recession on the dividend earning ratio of the companies, where beta is more during volatile market and compared to a normal market. Now what is the challenge? The researchers have argued on the basis of the empirical studies that the initial public offerings are undervalued in the market as compared to the seasoned equity offerings. How to introduce the above parameters, that is, how to introduce a variable representing IPOs and SEOs. IPO stands for initial public offerings and SEO is a seasoned equity offerings. Which is better? So now the concept of dummy variables come in. By using the concept of dummy variables, we will be able to identify which one is a better model, whether the IPOs are better or the seasoned equity offerings are better. So if you have a problem, research problem like this, so the regression model, you can introduce a dummy variable that if it is there, what is the scenario? If it is not there, what is the scenario? So the dummy variable are as follows. These may appear in our regression models because you have to include them in our regression models to find out the best answers of your research questions, that whether the IPOs are better or the seasoned equity offerings are better. So one in the form of intercept is there and the other is in the form of the slope. So you have to, this was the point where we stopped in the last here. So what next? The challenge of the day is it's related to a regression model or not. So now we are coming on to a basic concepts of assumptions. Assumptions in terms of never make them, reality is always more, much more worse. Violations means penalties. Violation of assumptions of classical regression models are there and they are immense. So we will be talking on them. Any model which has the assumptions is very difficult to justify, because in reality if you see the scene or the scenario behind it, you will always refute these kind of assumptions. So we'll be talking on these now. Let's quickly recall the assumptions of the classical regression model and let us refute these models' assumptions. Now the basic assumption was that the zero mean of the disturbances, that is the EIs, zero for all I's, homoscedasticity, that is the variance of the error terms, are also constant. Then we have the auto non-correlation, that is the uncorrelatedness of the regressor and disturbances, that is the covariance of Xi's and EZ's is also equal to 0, and the error terms forms the normality, that is with the zero mean and the constant variance. Non-stochastic regressor. The value of Xi is known to be constant in probability distribution of Yi, and Xz are not linear function of the other explanatory variables. So we have seen now the disturbances here. So what next? Our discussion is about the violation of assumption, which will be as follows. What are these assumptions? What are the consequences? How do we detect it, and how do we check that whether the violations are correct or not, or the assumptions are correct or not? So we'll do it one by one. Violation 1. The error term does not have a zero mean. So let's check out what it is. The violation of the assumption of OLS. It means that the expected value of the error term is not zero. What are its consequences? The error term does not have a zero mean. And what are the consequences? If the error term is included in the regression model, then this assumption will never be violated, and hence we should not worry about it. But if the regression model does not require an intercept and the error term is having non-zero mean, that means it may lead to serve the biasness in the slope coefficient estimates. So that means the first assumption is a problematic assumption in terms of if we do not have the error term mean as zero, then it may lead to some problem of the biasness as well as the slope coefficient estimates are concerned. Now let us see this on a graph. We are seeing here the violation of assumptions of OLS. So if the correct model is with the zero intercept, then the intercept and the slope estimates will be correct, and if the mean of the error term is not zero. So it's now the time to apply the basic problems. Let us have a look on this. We have a problem, estimation of a fixed cost and a variable cost. The total cost is on the left hand side and the quantity is on the right hand side. This is our sample data which we have to interpret. Now, as you have seen, when the quantity is 43, the total cost is 1239. When the quantity decreases, the total cost increases. Similarly, if you see upon quantity as 51, the total cost is coming on to 1303. So we have to think about this problem, estimation of a fixed cost and a variable cost. It's a problem and the sample data is in front of you. How do we do it? Now basically there are a lot of issues in relation to a total cost and finding out the quantity, and so we will apply this regression model. So just see this, y is equal to 7.650, which is a red line, and the other is y is equal to 4.437 xi plus 1693. So on the the x-axis we have the quantity, and on the left hand side we have the total cost. So what do we say after this? Now we hope to detect the assumptions and its violation. Now if the estimated model is having the intercept, then there is no need to test for such violation. So that means the presence of the intercept in the model will make no worries for us, and we do not bother whether the model is correct or not. But if the model is having no intercept, then we can simply perform hypothesis testing, and a null hypothesis, the mean of the error term is 0, and use a t statistics. Now we have to there is a software called eViews, so we have to go to eViews, we have to run the regression, and we have to find out whether the regression is up to the mark or not. So before we move on, let me give you a recap of what we did in the present lecture. We started with the concept of a linear regression model, that is the OLS model. We talked about the blue parameters for a particular parameter to be good or bad. Then we talked about the three variables, that is a control variable. We talked about the other indicators of how do we justify a particular model. So there were two indicators, adjusted R-square and the standard error of regression. And of course, in terms of the hypothesis testing, we see the overall test, F-test, and the t-test of the individual parameters. Then of course we saw that whatever are the assumptions of the OLS, they are under a question mark, and we talked about when to use a dummy variable, how to include it in the regression model. We can include it through two ways, one through intercept and the other through the slope. And we talked about that the regression model, if the introduction of the alpha is there, then there is no problem. We talked about the basic assumptions, which says that the error terms have a zero mean, they are homoscedasticity, that means the variance is also constant, and we have the non-autocorrelation, that is the covariance of the EIs and EZ is also equal to 0. Uncorrelatedness of regressor and disturbances of the covariance of I and J. We talked about the normality, and we talked about the non-stochastic regression. So I hope with all these concepts are very clear to you now.
With this note, thank you, ma'am. Thank you so very much for giving us this session. And friends, we will be back after a short break and would be discussing more on regression analysis. Hello friends, welcome to the CEC live lectures. Friends, as you know, we are talking on regression analysis. In our previous session, we discussed a lot, and as we promised that we will be talking more. So here we are with the discussion on regression analysis. For the discussion, we have with us in our studios Dr. Namita Rajput. If you wish to ask questions from Dr. Rajput on today's topic, then do call us through our toll-free number. Our number is 1-800-110-430. Now, I would like to request Dr. Namita Rajput to continue the lecture further so that our students are benefited.
So, we have talked in detail about the conceptual framework of regression, followed by the parameters, the assumptions, about the blue indicators, then about the refuting of the various assumptions. So, we will be now talking about the software using which we will be having more insights about how to refute, how to check, etc. So, we have a software called eViews which is frequently used. So, now is we have to go to the eViews, we have to run the regressions using the alpha and without the alpha, so that we are able to have the right statistics in front of you. So, the first is the run regression with intercept and find necessary statistics about the error terms, because it is all about the error terms which we have talked about, and the assumptions is all about the error terms, that they are following a normality, there is no correlation between the two, there is a zero mean, and there is a constant variance. So, now what is the learning? How to take care of such violations which we have talked about in detail. It is very important that you always have the error term in your model. So, the violation number 2 we are talking about now, the error term does not follow a normal distribution. So, how do we check it? Basically, it is assumed that the error term follows a normal probability distribution, and the violation of which it will mean that the error terms do not follow a normal probability distribution. Now, what are the consequences? Its consequences is that we are not able to use a t-test, the f-test, and the chi-square distributions for the hypothesis testing and the interval estimation. So, this is a big thing, and this has to be kept in mind. And if the assumption is not true and our estimates will still be blue, but we will find difficulty in performing the hypothesis testing and again the interval estimation. Now, coming on to the error term does not follow a normal probability distribution. One can see and judge whether the error terms follow a normal probability distribution or not by following tools. First, with the basic statistics. 2, by a graph, Q-plot and P-plot. Third is a histogram. Then we have Kolmanoff-Simron test of goodness of fit, and then we have a Jerky-Bera test. Now, we will be talking about the Jerky-Bera test. The Jerky-Bera test is all about the JB is equal to N, the brackets open S square upon 6 plus bracket open K minus 3 whole square divided by 24. Just see this diagram, this formula very carefully. When N is the number of observation, S is a measure of skewness, K is a measure of kurtosis. Because Jerky-Bera test is a test to test the normality, and in the normality either we have a skewness or we have a kurtosis. So, there is a threshold on this. The Jerky-Bera test follows the chi-square distribution with the 2 degrees of freedom. Now, we will take an example to have the basic insights about this. We have to assume that a researcher is trying to find out a relationship between the saving deposits and a commercial bank in India and a WPI, that is the wholesale price index. For this, he has collected the necessary data. You can see here, the left hand side we have the years. Year are from 70-71 to 1999. The saving deposits, as you have seen, is increasing with the increasing year. And then we have a WPI which is also increasing with the increasing year. So, using SPSS we obtain the regression results. Our basic question is whether the error terms is following a normal distribution or not. This is the summary results using a SPSS method to estimate the regression. So, if the table is in front of you, we have seen here the R square is coming on to be 0.96. Adjusted R square is coming on to 0.92. Adjusted R square is 0.918. and the standard error of estimate is 15,039.6. These are the predicators, the constant WPI. The dependent variable is a saving deposit with a commercial bank. So we have seen here, and how to interpret is that you have to see a significant value, that is it is less than 0.05. So here also we are getting a significant significant sig value. So which is again we are coming now on to the coefficients. The coefficients of WPI is also coming on to be a significant one, and T is also near to 1. And you have seen the histogram with the standard deviation as 0.98, the mean is 0 and n is 30. So the regression standard residuals and the dependent variable is a saving deposit with a commercial bank. So we have seen the descriptives. The descriptives is all about mean, median, mode, standard deviation, regression, kurtosis, etc. So again, if you see the test of normality on the screen, the significant value is coming on to be 0.01810 with the degrees of freedom as 30, and as far as the Kolmanoff-Simron test is concerned, the significant coming on to be, the sig value is 0.041. These are the results of the Jerky-Berra test, which is being highlighted on the right hand side of the screen. The Jerky-Berra is coming on to be 26.4 with the probability as 0.000. So how to take care of such violations? So this is a sheer violation. Is the non-normal distribution of the error term a serious concern for the researcher? No. If the sample size is large, and the central limit theorem will come on to the rescue. It will not be of any concern if we are interested only in estimates, especially the point estimates and the future prediction, nothing beyond that. If the sample size is small, then one may estimate any outliner in the data if it exists. It may ensure the normal probability distribution. Some transformation of the data may also ensure the normality of the error term. Now let us see this particular diagram. As you have seen on the the right hand side we have the observed value, and on the left hand side we have the expected normal value, and of course any outlier in this case. On the right hand side there is a point which is not lying on this, on the observed and the estimated. If we remove the outlier, we obtain the following results. The unstandardized residual is coming on to be 0.161 with the degrees of freedom 29. Significant is 0.054, and the Shapiro-Wick is a statistics of 0.972 with the degrees of freedom as 29, followed by a significant value of 0.64. So this is the violation of again the assumptions. So let us see the results before and after. That is, if we remove the outlier, is there an impact on this? So the two types of histogram are in front of the screen. On the left hand side we have the before one, and on the right hand side we have the after one. On the left hand side we have a regression standard residuals, whereas on the right hand side we have unstandardized regression coefficients. We'll take another example to clarify about the regression model without a log. So on the right hand side of the x-axis we see the regression standardized residual. On the left hand side we have a frequency. The series are as follows. There is a sample of 1192 with the observations, there is a sample of 192 with the total observations of 192. If you've seen on the right hand side of the screen, on the lower part of it, we have a Jerky-Berra of 6.31 followed by its probability value of 0.04. Now this is a regression model with a log, and in the previous it was a regression model without a log. So you have seen here the Jerky-Berra is coming on to 0.065 with a probability of 0.96. I mean, this is about transformation works for ensuring a normality. Now extending our understanding in this regard, that is, does the share prices follow a normal probability distribution, or does the return follow a normal probability distribution? This is our main question, and we would be talking on this. How do we do and see these points? Now, if you see on the left hand side, how do we do on this point? There is a histogram on the screen with a series of log that is the sample of 510 with the observation of 509. The Jacob error is coming on to 26.0 with the probability of 0.000. Now using R for normality test, we have to save this file and read it as a CSV file of sales and advertisement data.csv. This is the format under which you have to save that file. Now the data is equal to red.csv file chose. The str is the data and the attach you have to do the data. Running the regression with respect to advertisement and price, the output is 1M sales advertisement plus price and the summary is the output. You have to save the residuals so that the normality can be tested on the same. Now you have to load the basic and of course you have to make a histogram to see such graph whether normality holds or not. And the Jacob error test is the RESI with a ks.tst, that is the Resi P norm, and hence we have to end the program. Now we have to meet Mr. Econometrics in this, that is we are now testing the model. You've seen here the dependent variable is the sales, whereas the independent variable is the time. So the variable coefficient, standard deviation, t statistics and the probability is on the screen. Now if you see the adjusted R square, the sum squared residence, there is a 0.64 and it is 20.38. So it takes us to check another violation of whether the variance of the error term is not constant or not. This is the third violation which we are checking now. The variance of the error term is a regression model is not allowed to vary. If it is assumed that the error term has a constant variance and the assumption is known as the assumption of homoscedasticity, it means that with the change in the observation, the variation in the error term should not change. Its variation should remain the constant and does not have any kind of a tendency of any kind of a trend. It means that variance of xi, that is the error term or the noise, is equal to the variance. It's a case of a homoscedasticity. As you have seen here, the scatter plot of the residuals. So you've seen in this particular diagram that it's a case of a homoscedasticity. And now it is if the behavior of the error terms like which is given before, it is called a heteroscedasticity. So just see the diagram on the screens. It means that variance of EI is equal to the variance square of I. So on this particular diagram we call it as a heteroscedasticity. Heteroscedasticity may occur in many forms. So you can have again look on this. We have a discharge in centimeters, we have a poverty rate in 4th grade, and the above patterns also show the heteroscedasticity, and these are the various forms in which it may occur. So we have two cases of homoscedasticity and a heteroscedasticity. Now heteroscedasticity, what does it mean and why should I bother about it? If it is there, how do it concerns us and how do we see the impact, whether it does not impact or it does impact? If we have a heteroscedasticity in our data, the ordinary least square estimators will still be linear. Ordinary least square estimators will still be unbiased and consistent even if we have a heteroscedasticity. Now we have to talk about the various concerns of heteroscedasticity, that is if the data is impacted in the form of heteroscedasticity, what is the scenario? Ordinary least square estimators will no longer have the minimum variance, which means that they will not be efficient. As a consequence, they will also no longer be blue. And for an estimator, it is very important for us to have a blue estimators, but under these circumstances, this will not happen. Now, if we ignore the heteroscedasticity, what is the impact? For simplicity, let us consider the two cases. yi is equal to beta 1 plus beta 2 xi plus ei. The estimate of beta 2 will be beta 2 hat is equal to summation of xi yi upon sigma of x square I is equal to n sigma xi yi minus xyi sigma yi divided by n sigma xi square minus sigma xi square. With homoscedasticity, the estimate of the variance of beta 2 is equal to what? The variance of beta 2 hat is equal to variance 2 upon summation of xi square. This is with homoscedasticity, and on the right hand side with heteroscedasticity, the estimate of the variance of the beta square would be what? It is the variance of the beta hat square is equal to sigma x square, I sigma I square upon sigma of xi square whole square. So this is the difference between the two. Now we will be talking about if we have the heteroscedasticity in the data, what are the consequences? The estimates of the standard error will become biased and unreliable when heteroscedasticity is present. Mind it and listen to it once again. Estimates of the standard errors will become biased and unreliable when heteroscedasticity is present. This leads to a problem in hypothesis testing about estimators and other statistics and the confidence limits. To be precise, we can have a linear and unbiased estimator but not a blue estimator. So this is the problem that if the data is suffering from heteroscedasticity, we can have a linear and unbiased estimator but not a blue estimator. Now, a well-known econometrician, Ellison, puts the consequences of heteroscedasticity in a right way as follows. The reason OLS is not optimal when heteroscedasticity is present is that it gives equal weight to all the observations when in fact the observations with the larger disturbance variance contains less information than the observations with the smaller disturbance variation. Now, the concerns for heteroscedasticity. What heteroscedasticity does impact? Ordinary least square estimators will no longer have the minimum variance, which means that they will not be efficient. As a consequence, they will no longer be blue. Now, to be precise, heteroscedasticity leads to a very serious problem. Our estimated standard error are wrong. They are no longer efficient. Our conclusions from hypothesis testing and the estimators are wrong. Now, coming on to why heteroscedasticity. There are several reasons why the variance of the error will vary. The error learning model, as people learn, we expect their error to become smaller. In this case, the error term should decrease with the time. With an increase in the income, the comes in the increase in the discretionary income also. And in this case, we expect the error term to increase with the income. So this is why the heteroscedasticity is all about. So let us have the other aspects relating to it. The measurement error can cause heteroscedasticity. Some respondents might provide more accurate response than others. The sampling strategies can produce heteroscedasticity. Heteroscedasticity can also occur if there are subpopulations differences or other interaction effects. Effect of income on expenditure differs from rural people and urban people. Those on the larger income can purchase an essential component of the food expenditure and will also have left over the considerable amount of disposable income. Now, why heteroscedasticity? We have another 2 points. Heteroscedasticity can arise as a result of existence of outliers also. That is one of the figures which is not inconsistent with the other data. We call it as outliers. The skewness in the distribution is in one or more. Regressors may also call the variance in the error terms to vary. So there can be another reasons also. And of course, the misspecification of a regression model may also result into a heteroscedasticity. Now, the next question is how to detect the heteroscedasticity, because it can be a problem and affect the model of the regression also. Now, one of the methods how to detect the heteroscedasticity is a graphical method. Let us have a look on this. Take a scatter plot of the residuals against the explanatory variables. So you have seen here on the graph, we have a relationship between the saving deposits and the WPI in India. On the right hand side, we have the resident ID, that is the residuals, and we are here trying to show a relationship of the saving deposits with the wholesale price index in India. So you have seen the kind of a relationship which we are getting at the curve which we are getting. So if the sales and the residuals are, if you have a graph like this, what is your comment? Now, this is how we detect the heteroskedasticity with the graphical method. On the left hand side, there is no heteroskedasticity. Then if you see the second one we have, in the third also we have, in the fourth, fifth and sixth also we have. So this is how we detect the heteroskedasticity using a graphical method. How to estimate the impact of income, age and the number of kids in a family on the distance travelled during the vacations. So now the data is what? The data is all about the distance. On the left hand side, if we see, it is a distance in kilometers. In the middle we have the income per month, which is in thousands. We have age and we have number of kids. Why we supplement with the example? So that you are able to have a clear understanding of the various concepts using the comprehension and the power of the examples. They give you a clear insight of what we are trying to do. So here again, let us see again. The data is all about the distance, the income, the age and the number of kids. Now if you run the regression, the dependent variable is a distance. We apply a method of least square. The sample here we are taking is about 200. The included observation is also 200. So let us have explanation of the following. Then we have a variable, first is a constant. The coefficient is minus 39.1.54 with a standard error of 169. The t statistics is negative but greater than 2, that is 2.3. The probability is significant. If you see the age, again the probability is significant. In case of income, we have a significant p-value, and in case of the number of kids also the value is significant with the r square is as 34%, adjusted r square is coming on to be 33% again. Now these are the residuals versus the regressors. On the left hand side we have age, in the middle we have the distance, and then we have the income. How to detect the heteroskedasticity here? There are certain other models. We have, besides the graphical model which we have already done, we have a Spearman rank correlation test, we have a gold-fed Quandet test, we have a Glesjak test, Brejong-Pagon test, the Harvey-Gottfried test, the Park test and the White test. There are 7 methods here which we have discussed how to detect the heteroskedasticity in the following aspects. Now testing the hypothesis, the first test which we are taking here is a Spearman rank correlation test. Now what does it presumes? It presumes that the cause of heteroskedasticity is the error term has a correlation with x. To use this, we have to run the OLS and get the estimates of the error term. You have to take that x which is presumed to be correlated with the error term, you have to arrange them in either descending order or the ascending order. Then you have to calculate the rank correlation, and if it is significant, then there is a heteroskedasticity in this. Then we have the second method, that is the gold-fed quant test. This is applicable when the data is large. The test assumes normality and the serial independence of the error terms in the model. Now what are the steps? How do we have to calculate the heteroskedasticity? First, you have to arrange the data either in ascending order or in a descending order, followed by you have to select arbitrarily the central values and omit them from the analysis, and thus it creates 2 groups, one with the lower values and another with the higher values. Then you have to estimate using the OLS standard errors of both the groups and then apply the F test. Now, if you have done this method, just have a look on this. This is how we measure the heteroscedasticity using the Goldfeld quant test. Next, third test which is used to find out the heteroscedasticity in the data is a Brion-Spegon test. It's a test based on the logic that if a variance of an error term is not constant, the source of this is an explanatory variable. The variance of the error terms can be modeled as a regression model with the variance with the error term is a dependent variable and the explanatory variables are independent variables. The new regression equation is also called as the auxiliary equation, and the variance error terms is having no correlation with the explanatory variables, then the value of the coefficient of explanatory variables should be significantly different from 0. Now, what are the steps? The first is you have to run the OLS. Step 2 is you have to formulate the auxiliary regression of the residual squares of the x's. And the step 3 is a LM test. The LM test is of R square, and R square is the R square of auxiliary regression. Under H0 of homoscedasticity, the LM statistics is distributed as x square k. Alternatively, one can also use F test of auxiliary regression for testing the H0. Now the last test, that is the White test of heteroscedasticity. This is a test again based on a logic that the Bronc test is all about. It is in the auxiliary regression and equation is linear, but in case of White test it is a non-linear equation. The White test is still using an F or LM to test whether all the xi's, xj's and xn and xa's are jointly significant or not. So it is more generic and widely used test for checking the heteroscedasticity. Now basically how to check this kind of a scedasticity. This is the last thing which I am taking here. There are 3 approaches to handle the heteroscedasticity. One approach is derive a consistent efficient estimates of the standard error using White, consistent and covariance. And another approach is to use a generalized, that is the weighted least square method, and third is to deflate the variables. So I hope with all these things you will be able to find out what is a heteroscedasticity, what is a homoscedasticity, how these violations happen, how do we refute them, how do we tackle them, and how do they impact our model. So if you have a basic understanding of this, then you can see a tutorial and find out practically, because these are the theoretical backdrops which we give in these lectures, but you have to actually play with the data and see what happens exactly when the estimates are violated, the assumptions are violated, how to take care of these assumptions, how to find and detect the homo and the heteroscedasticity, what are its possible impacts and effects, how to counter them. So all these things will be more clear to you if you have a practical orientation of this. So with this, I think the theoretical backdrop is clear to you, and rest is your job to take care of the practical aspect, taking the fake examples, the examples of your own. N number of examples are available on the internet, so download them, play with the data, and the things will be more clear to you. With this note, I give the dice to the Gitika. Thank you so much.
Thank you, ma'am. Thank you so very much for the productive session once again. And friends, your feedbacks are important for us, so do write to us at info.cec@nic.in. We will be meeting very soon and would be discussing more under this series, Business Research Methods. Till then, take care. Goodbye. Thank you, ma'am.